Hi, my name is Salmi Pradhan, and I'm a senior at Lake Travis High School in Bee Cave, Texas. Today, I'll be presenting a brief summary of the work I did during my summer internship at Oswego Tech. First of all, I'd like to say I'm extremely thankful to my mentors, Ms. Ajita and Ms. Deepa, who are also co-authors on this paper, for guiding me through my internship and beyond, and giving me this opportunity to present our work at such a reputable forum like WASET. Without further ado, let's get into the talk, and I'll give you all a brief overview on a new linting philosophy, which we have creatively named yoYoLint. We fundamentally follow this mindset, BYOL, which is build your own linter, that changes the way the industry has been looking at linting so far. Traditional linting practices as promoted by big vendors are to kind of force users to follow a custom set of rules and qualify their design with these rule sets. There's hardly anything you can do as a user on the linting process itself, apart from running it, enabling it, and disabling it. On the contrary, in the open source world, there are good enough parsers available that allow us to build our own linters as per our requirements. It could be for system Verilog RTL, design test bench, assertions, DPI, UVM, you name it. In this specific case, we are talking about yoYoLint, and yoYoLint is a system Verilog RTL for yoSys. And yoSys is an extremely popular open source hardware synthesis tool, and it's used across the globe by a lot of academians, hobbyists, and even industry people. So with that, let's go to the next slide. To build a little bit of background, let's do a quick review of the global FPGA market. According to Market.us, the FPGA market is projected to grow at a CAGR of 13.6 billion. The forecast for this market in the next 10 years is to reach 39 billion, which is almost 40 billion US dollars, and that's only the FPGA, because of course there's a huge ASIC market in addition to the FPGA. To put the point forward, this is an extremely high growth area. Now, let's delve into a typical design flow. Here you can take an example of an AI acceleration engine that we want to build on an FPGA. Once the architecture is done, the first phase is the design entry in RTL, like System Verilog RTL. You enter the RTL design, and then you validate the design in System Verilog Test Bench, UVM, etc. by running simulations. Once you're convinced that your design is good, you take it through a synthesis step. This is where yoSys fits in. In post-synthesis as well as pre-synthesis, we do verification, and once it's all kind of agreed upon, then we go into a design implementation phase and take it all the way down to an FPGA through a bitstream file or through an ASIC process. Now, with advanced technology nodes, the cost of SoC or system on chip design is skyrocketing. It can be anywhere from 1 million to 100 million, depending on the kind of chips that we're designing, the technology node, and the complexity. And if you do look at the right hand side of the slide, you'll see that DERPA has forecasted the typical costs that go behind building a chip. And you do see that team costs are high, and so are the costs of EDA tools and servers. These costs are associated with sophisticated design languages like System Verilog, VHDL, etc., working on advancing EDA tools and IPs. This is where open source technologies can play a game changing role in addressing some of the cost challenges in modern chip design. Now, open source technologies like Build Your Own Linter can come to our rescue. They enable us to build tools that we need, and they're completely scalable to our own requirements, easy to adopt, and no longer are you stuck with these kind of all you can eat deals with your big EDA vendors and no one size fits all mindsets. Because when it comes to FPGAs, we are into various kinds of design sizes and mindsets, as well as the requirements. Here is where open source can really help you, and build as you go is kind of the mantra that we followed. So fundamentally, we do want to use available vendor tools, but if something is missing, you don't want to have to wait for your EDA vendors to add it. You can go and add it in yourself. This could be your system Verilog test bench linting, assertion linting, UVM lints, DPI lints, or it could be the yoSys lint that we're talking about, yoYoLint. It promotes your brand and attracts talent at all levels, even talent like myself at the high school level, especially because of the low barrier to enter and contribute. This helps to foster more innovation and continuously improves the ecosystem. And we can also use it with CI/CD flow which is basically the continuous integration, continuous development flow. And best of all, this is possible because it's all done in Python and other similar languages. The result is a potentially vast and very diversified skilled workforce, which is now being built with open source development. And now, with all of that established, let's learn a little bit more about yoSys itself. So, what is yoSys? I'll keep it very brief because it is extremely popular. It's an open source synthesis tool for Verilog, System Verilog, and VHDL, and it converts an RTL to gate level netlist. It does many other things, but from our perspective, that's what we're going to be focused on. It supports ASIC and FPGA flows, and due to its versatility, it's gaining traction and popularity in the industry and academia. So let me go over a few of the key features it encompasses. It does technology mapping optimization, and it also supports formal verification. It's quite modular and extensible with custom plugins and scripts, and it's completely tickle driven. It's also very popular in the open source hardware, for example, Open Hardware, and OpenTitan is an extremely popular hardware chip that is available as root of trust design from Google, and it supports yoSys as well. So yoSys has been used for quite some time in a lot of places, and its adoption is growing as part of full open source EDA tool flows such as Silicon Compiler and the Open Road Initiative. Essentially, yoSys is becoming an integral part of these open source flows. Okay, now the next question is why yoSys? It's important to understand why yoSys is extremely popular and why it was the tool of our choice for this work. First and foremost, yoSys is extremely lightweight. It's only 14-15 megabytes in size compared to 60-70 gigabytes for vendor charged tools. On LinkedIn, it does have a big following and there are many people recommending yoSys. I'd like to quote two examples from our community colleagues in Sweden, where one design takes about 2 seconds in yoSys versus a minute with vendor tools. That's 30 times saving in terms of time with yoSys. Second, it's extremely user-friendly. Citing a LinkedIn post from Franz Garman, who's a PhD student, as per him, he was able to put it in a complete RISC file design using yoSys within a minute, which is extremely fast. Also, it's widely used, it's community-driven, just like how we're talking about it, and there are many efforts happening across the globe to extend yoSys for different applications. Now let's discuss why should we lint RTL code. The whole idea is to find bugs early. Whatever low-hanging fruits you can find using linting, we should. It helps us to do a shift left, which fundamentally refers to a concept of finding things early on that saves you time and cost. So for a moment, you can look at the curve on this slide. You see that the cost of finding bugs and fixing them with static analysis is 6.5x more, right? And the cost of actually starts increasing exponentially from there onto later phases of testing to actual deployment. So the sooner you find the bugs, the more cost effective it's going to be. Further, it also keeps the code compatible across tool chains. That's the key reason why we want to build our own lint tools, because there are things that are specific to our design flow, and build your own linter really helps you in this context. It integrates easily with CI/CD, continuous integration, continuous design flows. The idea is now that it's open source, it's completely free of cost. So you can actually scale up and scale down as much as you want without worrying about your EDA budgets. And further, the linters are available for many things. They're useful to users for System Verilog RTL, System Verilog test benches, and that are complex class-based test benches. Also UVM test benches or UVM code-based assertions, System Verilog assertions, and also acceleration, emulation, formal verification, etc. So what we're saying is that linting is not necessarily restricted to RTL. It scales and goes far beyond all of this, and it's possible today with open source platforms, such as the one that we are going to show you. And this is where SVGO really helps customers to build various lint tools on a BIYOL model, which are customized for specific use cases for teams. So here's a quick recap of System Verilog RTL design constructs that are synthesis friendly. This is just a subset for illustration purpose. Some of them are type def, logic usage, enumerator types, structs, packages, interfaces, etc., etc. Again, this is not necessarily an exhaustive list, but this is kind of what the focus is on for this specific tool chain. So, what is the yoYoLint approach specifically? yoYoLint is built on top of PySlang, and PySlang is a Python binding on top of C++ parser called slang or slang. Slang, a complete system Verilog parser in C++, is completely open source. On top, there is also PySlang, over which we have built something called PySlint and yoYoSlint using Python-based rules. Basically, we write rules in Python to talk about system Verilog RTL code. So on the left-hand side, you can see the code snippet. There are a bunch of defs, as you would imagine in Python. And you could also see the interface declaration, data declaration, parameter declaration, etc. In a typical system Verilog code, these are natural flow, meaning that there is an interface construct, there is data declaration, there is parameter declared, etc. We kind of identify the rules. Each rule emerges from user case study. The user can come back and say, okay, I want to have this as a good rule for checking my design. And then we basically go and implement it along with the messaging API. We call it YYL which is yoYoLint message. And it's a common API or function available in Python in our Python library to say that we would want to issue a message through a standard mechanism and through which we identify what is the lint violation. So the whole idea is that we build a framework and we provide this as a minimalist rules as case studies. And we help customers build on top with their own rules. So they don't really have to even donate back. It's all an MIT license, and it can be proprietary if need be and customize the existing rules, which is also possible. And you can also add newer analysis tools or apps on top. So it's not intended as a traditional EDA product, and it's not something that we intend to license and then give it to customers and start making money from it. It is an open source idea. Rather, it's like an open room for innovation, and it's built on a solid data model. In the case of Verilog, we probably call it VPI or a very low procedural interface. Think of it like a model that allows you to walk through your system Verilog RTL code, construct by construct, line by line, in a very structured manner. And that's what you see on the right-hand side. You see that if this declaration is a data declaration, then we go and say, hey, if your data type is int, then it's not supported. Integer is supported, int is not supported. On this next slide, you can see yoYoLint in action. Upfront disclaimer, based on the feedback we have received so far, we know that we need to modify the way the analysis is presented for easy readability and formatting, and the Oswego team is actively working on that. But the idea is we want to show what happens with a typical system Verilog RTL code when you run it with the most recent version of yoSys. Here we show 4 or 5 tests that we ran, and you can see various errors that say syntax error. For example, unexpected token ID error, or the next test gives syntax error with unexpected semicolon, and the third one says syntax error with unexpected token ID, or expecting equal symbol, and the last one says syntax error, unexpected token ID, expecting a comma or something. So the point we're trying to say is today, if you run your existing system Verilog RTL code with yoSys, the chances are you're going to get errors like this, which are harder to understand from a pure designer perspective. And this is expected from typical computer science or parser perspective. It's technically correct. It's just that it's not something that's easily actionable for a general system Verilog RTL design engineer. Now, if we do the same test, and by the way, this is the exact code and log files are available on our public repo, you see that we ran the same test with yoYoLint on the log files, and you see that fundamentally it goes and shows that int param is NYS. NYS, by the way, is an abbreviation we use for not yet supported. So if it's not yet supported by yoSys, then we capture it as a rule in yoYoLint and flag it to the user to say that, hey, your code contains this usage. This is not supported in yoSys, and so you're likely to end up seeing a weird error message that you found above. So if you want to avoid that, fix it before you run your system. The idea is customers run yoYoLint first, and once it runs clean, then you take it to yoSys. And just to clarify, we aren't really building on top of a yoSys parser. It's a completely different parser, which is a slang and PySlang based parser. So the chances are that we don't have the same limitation that the other parsers have. In other words, we build our own completely independent linter to capture the rules for yoSys based on slang and PySlang and PySlint. This slide shows the currently available set of identified system Verilog rules. Now, this is just a snapshot, not necessarily the latest and greatest, and each of this has a corresponding issue opened at the yoYoLint repo at the svigo GitHub repo. If you go to github.com/svigo/yoYoLint/issues, you will find each of these documented with specific rules, as well as a specific small unit test that describes the problem. So these are just the current set of rules. It's not exhaustive, and we strongly request and encourage users and the listeners of this talk to go and try out some more stuff and say if you believe something is not supported in yoSys and it's not already captured, please open an issue in our repo. We'll be happy to add this support in yoYoLint. Another quick note, not all of this is already captured. And at the time of this talk, the idea again is, as I mentioned, yoYoLint serves as a platform, as a case study with a minimal set of rules, and users can add more rules, and if time permits, of course, our team would be happy to add these rules as we go along. So now specifically, this is a small table of what the feature and the description, and a very brief one of that. So for example, a couple of problems we run into are that enums inside modules don't work today with yoSys, structs usage as signals and ports don't work, multi-dimensional arrays or MDAs are not supported, the type defs for data types are not supported, packages, there are severe restrictions on using packages. For example, importing anything from a package is not really supported. Streaming operators are not supported. For example, using the inside operator and the case treatment is not supported. Mark ports are not supported, and I could go on. So let's conclude this talk with a summary for BYOL. Again, we want to re-emphasize that we are not claiming this as a complete EDA product. It's rather build your own linter as an open source effort. We started small, then started adding rules, and we open sourced it so that users can add their own rules. And we strongly believe that it's an exciting new frontier that's opening up, and we make it many new frontiers, as in plural, because RTL design is not the only thing this approach is applicable to. In fact, our first flagship products in this platform are targeted towards system Verilog test benches, which are using class-based as well as assertions and UVM, DPI, etc. And we borrowed the same idea for yoSys because a lot of engineers in Europe specifically do use yoSys for system Verilog designs. And this is an interesting concept, and we believe it's going to expand further in terms of use model, and that's why we are overexcited in terms of what we're going to do with it. yoYoLint as a new innovation is coming out, and for a while this is in the EDA market. People say that the innovation is in debt, but thanks to the new open source model, innovation is back. Open source is now leading the way for commercial tools to follow. So with that, we would like to see what more Lint capabilities you would build on top of this. It's kind of an open invitation from svigo to innovate. So once again, please come up with your ideas, and then whatever you want to contribute to the open source, please feel free to do so, and anything specific to yoSys and yoYoLint, we will be very happy to look at and work together with you. svigo is taking leadership and initiative in this domain. It's a great place to work, and my experience with svigo as an intern has been nothing less than amazing so far. So my mentors, Ms. Ajita and Deepa, are not only very knowledgeable in their domain, but also some of the best human beings I have come across. Open source initiatives need people like them to promote its adoption and give opportunities to young people like me. So thank you for allowing us to present our work in this community. And once again, my sincere thanks to my mentor and guide in this work, Ms. Ajita and Ms. Deepa, who will once again come to my rescue and field all your tough questions. So thank you so much for listening to this presentation. With that, our team is ready to take some questions.